Eureka Webinar in association with Rutland Plastics. My name is Paul Fanning and I'm editor of Eureka. Today's presentation is on design for plastic injection moulding and will be given by Stuart Johnston, director of Rutland Plastics. Before I hand over to Stuart, however, I should just say that if you have any questions during the presentation, please type them into the box on the right-hand side of your screen and we'll endeavour to answer them at the end. If we don't have time to answer them or your question, we will hand it on to Rutland Plastics and they will answer it for you offline. And with that, it just remains for me to hand over to Stuart. Stuart.
Okay, thank you, Paul. Thanks for the introduction. Let's start with a little bit of an overview of what we're going to do. So we're going to talk about mold tools, material selection, and then some of the aspects of design and some of the common defects that we see with plastic design. But as a bit of background to that, let's just have a little look at Rutland Plastics ourselves. Who are we? So we're a trade injection moulder, founded way back in 1956. And we're still a privately owned business, and that's very, very key to the ethos of the business and the way that we work with our respective customers. In terms of the sort of size of business we are, well, in 2023, we hope that we'll turn over around about £17 million, of which about £1 million of that will be new tooling that we commission and project manage on behalf of our customers, some of which will be made in-house in our in-house tool room. We work with a large number of customers and markets. We have a background in utilities, specifically sort of water and gas piping and electrofusion products, which are quite a technical way of welding plastics together. But we do all sorts of other stuff like lightning conductor systems. Medical and invalid aid is a growing area for us. Medical now comprises nearly 20% of our business. We do lots in electronic casings for all sorts of different applications, and increasingly, actually over the last sort of 5 to 7 years, consumer goods, which would have traditionally been made in the Far East, and now customers are looking to make these in the UK. All of this is backed up by our various accreditations and memberships, 9001, which most people will be familiar with, but 14001, which is an environmental accreditation, and crucially 13485, which is our medical accreditation, and actually really drives the quality system across all products at Rutland Plastics. We are investors in people, and our colleagues here are a crucial stakeholder in the business, as are our suppliers, hence why we're a member of SEDEX. And you know, we really value the memberships that we have with the GTMA on the tooling side, British Plastics Federation being part of their trade moulder group, and Made in Britain, which obviously we're very proud of also. So as a business, what do we do? So I thought I'd share with you the Rutland Plastics mission. Slightly cheesy, these things sometimes, but actually, you know, it does tell you who we are and essentially why we're taking part in this webinar today. You know, we want to work in partnership with our customers, and many of our customers have been with us for, you know, many years, some 35, 40 years, and we've worked with them to help them achieve their goals through various iterations of their product range, helping them successfully take them to market, refine them, make them more efficient, and then also develop the next generation of that product. And we're a business that you know, we focus on the manufacturing side of the business and becoming as efficient as we possibly can, but really getting involved with our customers from a technical perspective. And we see our substantial technical team as an extension of our customer. We want our customers to use them and use them for the benefit of their business and their products. But within that, you know, we want to grow our people, we want to grow our colleagues, and we want to do all that we do with taking pride in things. You know, we want to do the best job that we possibly can. And that's a nice lead into what we're talking about here. So where do we start? Well, we start with mold tools. Now at Rutland Plastics, we have our own in-house tool room, and we work with various suppliers in the UK, in Europe, but also in the Far East. And then the mold tool is a key part of the the selection process. Now, this isn't an exhaustive list, but what we've got here is a bit of a basic explanation about some of the steels and metals that can be used for choosing an injection mold tool. So at the bottom end, we've got aluminium. Aluminium is suitable for low volume projects where the plastics aren't aggressive. So what we have is fairly sort of non-abrasive materials that flow easily through the tools, don't require much pressure. And then we move from there into pre-hardened steel. One common type is P20, and we would call that a semi-hard tool, somewhere in the region of about a 35 to 37 Rockwell. And this is really good for medium volume projects. Now, what do we call a medium volume project? Well, for us, that would be a project where the tool has a trouble-free life of about 250,000 shots. That's in comparison perhaps to aluminium, which would be around 50,000 shots. But when we say trouble-free, that doesn't mean that's the end of the life of the tool. The tool will go on a lot longer than that. It just requires care and it requires regular maintenance, and that's something that we do take a lot of pride in. We then go from there into H13 steel. Now, H13 is a fully hardened tool, so we're talking sort of 52, 54 Rockwell hardness, really appropriate for high volume projects where the materials are abrasive, so perhaps with a glass fill, where high pressures are required, and also where there's some complexity and there's perhaps a lot of moving parts in the tool where the steels are rubbing against each other. Again, these are more expensive, but they are fit for purpose when required. And at the top end, you have a stainless steel option, which is again for higher volume projects, but it gives that sort of really superb surface finish, often used for mirror polished parts, so clear lenses and the like. And as part of that is corrosion resistance. So obviously there was a reduction in maintenance time. Now, the last point on the slide is quite critical, because actually when choosing the mold tool, it's important to think about, well, how high volume will my product be? How complex is it? And what do I want from this tool? How long does it need to last? And those are very, very subjective questions, because actually it depends on your business case, it depends on your product, and how that project's going to evolve. But that's something that we can help with. And as part of helping with that, we have developed a guide, just quite a simple table on our website, which tries to explain the different properties of different metals when used for injection mold tool. And this is again really part of the ethos of Rutland Plastics, because we want our website, we want our communications with customers to be educational, we want them to be informative, and we want to try and help you develop your project and move it in the right direction. So you'll see more of this on our website. Once we've chosen the tool, another factor is obviously the material. Now, again, this isn't an exhaustive list. We've just selected some basic materials here, which you might want to think about. The most common being the polyolefin family, which consists of polypropylene and polyethylene. These are the most commonly used materials in the world for all sorts of different containers and kitchenware, pipe fittings, most things that you would use at home, whether it be for a food application or something, would be made from a polyolefin, and those are easily recycled, and that's one of the good advantages of these materials. But they are reasonably priced. They are commodity materials, and they are very good for what they do. They're non-abrasive. They flow very easily through tools. Therefore, they influence the selection of steel and the decisions that you have to make on capital investment. But then you can move more towards aesthetic materials, such as ABS. Now, ABS is a very common material in terms of household appliances and can be easily mixed with polycarbonate, which is an engineering grade of material. But this would produce tough, very high gloss, very aesthetic looking products. Some examples here: domestic appliances. Well, something like a Dyson vacuum cleaner is a lot of ABS. There's a lot of polycarbonate in there as well. Car fascias, interior and exterior, and also computer and electronics housings. Sometimes, again, required with additives or with a mix of polycarbonate if specific temperature requirements are there, or perhaps there's a flame retardancy requirement for some kind of industry regulation. And then we have nylons. Now, nylons are a very, very useful engineering grade of plastic, and commonly used with glass fill in them, because they have often been used for metal replacement projects. Yeah, so these are products which would have been made from metals, very expensive in terms of the raw material, but also very expensive to manufacture in numbers. Very good temperature properties, so rigid, hard wearing. And again, gears, bearings, and automotive underbonnet requirements are often made from nylon. Now, again, you can find more information on different materials available on our website. As I said, this is a non-exhaustive list, but we do cover most of them on the Rutland Plastics website. And just a bit of an example there, because I've mentioned metal replacement. This is an example of a hydraulic filter which is used in large commercial industrial vehicles. This is a product for a customer called Chainings, and this product would have been made from cast iron and would have been very, very costly to manufacture. We worked with Chainings, and the project took a couple of years to get off the ground, to help them move this to a plastic product. And that was quite a tough call, because not only did this part need to be incredibly strong, but it also needed to be very dimensionally stable. And that's dimensionally stable when it comes out the injection molding machine, but also for the life of the product, and also when the product is operating in its working environment. Crucially, at Rutland Plastics, not only do we work closely with our clients, but we also work with our supply chain. And we involved one of our material partners and identified that this product, because of its requirements, not only did it need to be an engineering grade of plastic, such as nylon, but it needed to be a specific long fiber glass additive, which was put into that nylon to give it its required rigidity, to give it its strength, to give it its dimensional stability, and to make sure that it was a product which could withstand the extreme sort of conditions of its working environment. You'll also notice on the part as well that it has some metal inserts which were required for assembling the part. Again, because the material is nylon, it has a high melting temperature and it's glass filled. Rather than these be heat staked or tapped into the plastic molding, these are actually ultrasonically welded into it, because that such a high level of energy is required. But a very successful project. Now, the environment is critical when we're starting to think about plastics. And it's really important from a design perspective to think about this. And it's a huge focus for our team. Our design team work very, very closely with our customers, and we've kind of coined the phrase reduce, reuse, and recycle, because there are many ways you can approach designing for environmental concerns. So just taking these one at a time. Reduce. So our design team, we have a team of 3 product designers, all of whom have come through high levels of training, so bachelor's degrees, master degrees, to help our customers with this sort of work. They will work with the customer to try and make sure that as little plastic is used as possible. Okay, one of the key things about environmental issues and waste is to take as much of the raw material out as possible. And one way of doing that is through smart design. Yeah, many years ago, often things were products were designed as sort of thick and chunky, and it was seen that that would give them strength. Well, actually, that's not the only way to give strength. Often smart design, such as ribbing features, or perhaps using additives in the plastic material itself, such as glass, mineral, and natural fibers, can help give strength, and help remove plastic from that product. And that makes it a more environmentally friendly product. You also want to try and reduce the amount of energy required to make the part. When you make a part that's very thick and has lots of plastic in it, or perhaps the material is overspecified, you have to put a lot of energy into melting that plastic and actually molding the part, and then cooling that plastic to get the finished piece. Again, you can reduce that, through smart design. Reuse is something that also should be thought about. What is it you want to reuse? Can the product itself be reused? A critical question for our customers, something that we try and ask them, is, what do you want for this product at the end of its life? And that's going to be different for every product. Something that's single use will clearly be thrown away, and the customer will want that to be easily recycled. So that will drive material decisions in that product. You will want to look at materials such as polypropylene, because if it's single use, it can then easily find its way into a waste stream. At the other end of the scale, you might have products that have a lifespan of 10, 20, 30 years. So it's all about durability. And even if you're choosing a material that's not easily recycled, in 20, 30 years, those recycling streams may be available. But it's like a key question to try and think about: what do you want for that product at the end of its life? And can you use a recycled material to make the product? Now, when I say recycled, it's important to differentiate between reprocessed and recycled. Recycled can be a sort of chewed up plastic into granules, which is created from waste products. Whereas reprocessed material is material which has been chewed up, but re-extruded and done in such a way that it's delivered with a technical data sheet, and therefore legitimately has properties that can be measured and comes with a level of quality. And we would always encourage the use of reprocessed material as opposed to purely recycled or reground. But critical question: can reprocessed material be used? Now, very difficult if it's a food application, and actually very difficult if it's an aesthetic application, because by nature of the fact that the material is reprocessed, it won't look very good. It may function, but it won't look very good. But if it's something that's hidden, if it's something that's under bonnet or an internal part, it's something that should be considered, because again, it's a very good way of trying to reduce the carbon footprint of the product. And then recycle. So again, going back to, how do you make it easy for your product to find its way back into a waste stream, and then from that waste stream into a reprocessed material, and then back into another product? So again, design can play a huge factor in this. When you're putting inserts and screws into parts, often those hamper the recycling process. Recyclers and reprocess, they don't want inserts and screws because it's a contaminant, and it actually damages the equipment and the machinery that they use for recycling. So we'd always encourage our customers to look at snap fits, look at other ways of joining parts together, and that's a key thing that our team can help with. Also, avoid sort of bonding using glue, and particularly using glues that bond different type of polymers, because actually where you put two different types of polymers together, whether it's through an overmolding or it's through a bonding with an adhesive, effectively what you're doing is you're creating contamination, because in the recycling stream, it's then extremely difficult to separate those materials. So again, we would really work with customers to try and provide design input that allows them to use a single grade of material or parts that can be easily separated to help that recycling process. And finally, similarly with decorative paints and lacquers, often they can be a contaminant into that process as well. And where possible, how can we work on the design? How can we work on the tool in conjunction with the customer to try and make that part the finished article, so that we don't need paints and lacquers and coatings, so that part is as aesthetic as it possibly can be. Which leads us on to quite naturally into bioplastics. And bioplastics are a massive topic, and they come in many forms. But I'm going to jump to the last point on this slide here, which is bioplastics aren't the answer, but they are part of the solution. And what I mean by that is that, bioplastics should be treated like any other type of plastic, and indeed any other material that we have in the world. They require energy, not only to make them, but they require energy to process them, and they also require energy at the end of their life in terms of what you can do with them. And that's the same whether it's metal, it's glass, or it's what we call virgin plastics that come from crude oil and gas. But indeed, you should think about them, because there are some very good bioplastics out there. And again, there's more information on our website, which looks at plastics which use natural fibers. So again, if you have a product which you're looking to reduce the amount of plastic in it, one very effective way of doing that is by using a hemp additive or a wood additive in that polymer, and that could reduce 20% of the plastic, take it straight out of the part. Does come with its downside. Obviously, a huge amount of energy has had to go into growing that natural additive, in terms of the land that it uses and the industrial processes and fertilizers that are used. But it could be right for that product, and it's something to think about. Another one would be compostable plastics. Very important for thin plastics such as films. If you go to the supermarket these days and you buy your veg, and you have your veg in a little bag once you've picked it, that bag can go straight into your composter. But it's very difficult with hard plastics to compost it. And again, that can often only be done through recycling in industrial composters. So again, if you were going down that route, you have to think very carefully about, well, if that product is a hard plastic and it needs to be industrially composted, how do I make sure the consumer or whoever is in possession of that product can get it easily into that recycling stream? And at the moment, that is very difficult. And what we don't want is those sorts of plastics going to landfill. So sometimes actually bioplastics are not the answer. Sometimes a virgin plastic is the answer, because it can be more easily channeled towards a recycling stream. But again, there's more information on our website with regard to bioplastics and the various pluses and minuses of them. So just going back, taking a step back a little bit, design for economy. So again, this is an environmental issue, obviously, because what we want is we want our customers to not only design parts which have as little plastic in them, because they have a reduced carbon footprint, but if they have as little plastic as possible, they are much more efficient to make, and they are much more lower cost, which is to the advantage of everyone involved. Some of you will be aware that when you're designing a plastic part, the thicker the plastic is, the more energy and the more cost there is. Now that cost comes from many different areas. It comes from the fact that you're using more plastic, and plastics are expensive, but also because thicker plastic requires more energy to melt, which extends the cycle time of the machine, and then requires more time to cool. So again, we want to try and think about reducing the amount of plastic, reducing the thick sections, looking at where two plastic parts are used and perhaps one would do. Again, looking at snap fits and where we can reduce mechanical fixings, and also avoiding secondary operations. Where can we make a product using one process, one injection molding process, rather than taking something away and perhaps having a secondary manual operation to fix them together, or a gluing operation, or perhaps even welding. So we've got to think about that entire production process, the design of the part, and how to get that as efficient as possible. You also need to think about the efficiency of the tooling. This shouldn't be underestimated. And again, it's a very subjective area, as I said before, because it's all about return on investment. But how do you get the number of tools correct? Where is it possible to combine different parts into one tool, and where is it appropriate to have one tool that has multiple cavities, so is making many of the same part at the same time? And again, this is something that our team can help with, because we can help you work out the payback on various different options, because these need to fit with some big investment decisions that customers are making. A similar thing could be said for hot manifolds. So standard way of injection molding is to use what's called a cold sprue. So that's where the plastic is fed to the part, and effectively it's a waste piece of plastic which comes from the inside of the tool. It can be recycled, but energy has been used, plastic has been used, and it is wasteful. The option which counters that is to use a hot manifold, which keeps the plastic in a molten state until it reaches the product. What that means is that you don't have that waste sprue, but it does cost more. So again, there is a return on investment and an environmental question to be asked there, which our teams can assist with. And there's a point in there about heat conductive alloys. Standard tools are made from aluminium or steel, but there are other metals which can be used within tools which will help reduce cost. Now, when I say reduce cost, the alloys themselves add cost into the tool, so it's a more expensive tool, but they will actually provide a return on investment because they have enhanced heat conductivity. So they will reduce the cycle time of the part by drawing heat out of it much quicker, and make sure that tools can produce a higher number of parts. So, for example, this could be the difference between a tool which has one cavity or two cavities, or indeed having one tool or two tools. If you can speed up the cycle time by using the right conductive alloys, it could, not only have a better return on investment for the tooling, but also have a lower impact on the resources used in that manufacturing process. So just moving on to some of the common defects that we see with injection molding. Now, these are the first one to start with, I suppose, is sink marks. We mentioned before that a very efficient way of trying to use less plastic and be smart about design is to use ribs. Yeah, so rather than have thick plastic to give strength, use a ribbing structure on the underside to deliver those properties. But often, if those ribs are too thick, what it will do is it'll produce a sink on the top of the part, often on the aesthetic A face, which is quite unsightly. And that's because when plastic cools, it starts to shrink. Where you have those two faces coming together, as you can see on the picture on screen, this creates a sink mark. So again, this is something that our team work with our customers on. And one of the general sort of guides that we would have is that the rib itself should be no thicker than 2/3 of the face that it intersects with. Yeah, but often that is a very general rule, and sometimes it doesn't deliver the right strength or the right shapes that customers require. And that's really where our team come in, and they will help customers design that ribbing structure, not only to deliver the aesthetic side of things, but also the strength and mechanical properties of the part. Sticking with the theme of thick sections, and perhaps using thick sections to deliver strength. Another problem is voids. So again, as you'll see on the picture on the left-hand side of the screen, when plastics, as I said before, when plastics cool down, they shrink, and often that shrinking process on a very thick section will create a void, and that it's effectively an air bubble inside the plastic. Now, that's not something that's advisable. One, it's a waste of plastic having that huge thick mass there, and it's a waste of cycle time and all the energy processes that go into manufacturing. But equally, it can affect the mechanical performance of the part. So it is a weakness, and you could see problems coming from those areas. But equally, if it's a part which needs to be machined or worked on afterwards, those voids would be seen as you started to machine into the plastic, and that level of inconsistency is often problematic. So again, we would work with customers to try and reduce that thick section, look at ribbing structures, look at ways of coring out, not only by using design, but also by using features within the tooling to deliver that. And weld lines, again, another common defect. Plastic flows in its molten state. It's a liquid, and when you have a feature, as you can see on the on the screen, when you have a feature such as a cutout, the plastic will flow from one end of the part and needs to flow round the cutout, and it joins up at the other side. And this is where we get a weld line. And we get a weld line because as the plastic flows round this feature, it's cooling down. So when it gets to the point where it meets and the two melt fronts come together, the plastic isn't as molten as it was. And again, it creates a visual effect. So the weld line can often be seen, and it creates a weakness. Now we can work with the customer to try and modify the design to minimize that. There are ways that we can minimize the effect of weld lines in the tool, but they are a natural feature of injection molding, and it's something that needs to be considered, and it's something that we would work with customers when we go through the design for manufacture process to try and firstly identify, but secondly mitigate any risk that comes from them. And burning. So burning, it's a problem which applies to weld lines as well, because obviously what we find with burning is it's where the last point of fill is, or it's where the plastic is moving the gases that are inside the tool. Because when we melt plastics, it creates gas, and that gas has to go somewhere. So what we can see on the diagram here is where burning has come at the last point of fill around these very small ribs around the boss. Equally, this could happen where we have a weld line as well. Again, it's something that we have to work through a design for manufacture process. We have to identify where the risks of burning are, because it's pushing gas, so we have gas traps. We have to look at how we can vent that. We have to look at how we can design the tool such that the tool will expel those gases and minimize this sort of risk, because not only is it unsightly, but again, it does affect the mechanical properties of that part. But these are all standard things that we work through. And a bit of a design tip, because often when we have problems with something like a weld line, and a weld line is something that will always be there. If there's a feature in a product, a weld line will always be there. It's just a matter of how easily you can see it. One way of disguising it, one way of reducing the visual impact of it is to use a texture or some kind of chemical etch on the tool. So here's an example of a sample molding that we have to talk to our customers about, but it goes through the various VDI scale of texture finishes, and this is one which would be delivered through a spark erosion process, but equally there are many other textures which can be applied through a chemical etching process that will help just improve the aesthetic of the part, not only hide some of the imperfections of something like a weld line, but actually genuinely give it a nice finish, whether it be a leather effect or a nice satin effect, or in the case of a very, very rough VDI, it might deliver some kind of property to the plastic part that's crucial in its function. So that's really it in terms of the overview of design for manufacturing, and I understand there may be time for some questions.
Yes, absolutely. Thank you very, very much, Stuart. Yes, we have a few questions. Let's start with crack on with them straight away. How do I know if I have the right number of cavities in a tool?
Okay, yeah. Yeah, I mean that's a good question, because often when we're talking about cavities, it could be a tool that has a number of cavities, but each cavity makes a different part, or it could be a tool that has a number of cavities, and each cavity makes the same part. And of course, it goes back to my point earlier on, which is about return on investment, where the product is lower cost or lower volume. Often it makes sense to put different parts in one tool. So you've got a number of cavities, each making a different part. That's a very low cost way of approaching things, but it does come with some downsides, because what it means is that the plastic needs to be fed through that tool to parts which sometimes look and weigh differently. So one part's heavy, one part's light, or it could be that one part has a high aesthetic finish and the other is an internal part, and it's very different to get that balance. And when I say balance, it's a balance of ensuring that plastic flows through the tool in a balanced way to deliver everything you need to parts that are actually quite different. But sometimes that compromise is worthwhile if it's a low volume or a lower quality product that we're talking about. If it's an internal part, often the aesthetic's not as important. But equally, at the other end of the scale, it could be a return on investment in terms of how many parts will I need per annum, and how do I want to I suppose maximize my return on investment. Often, if a project is higher volume, a multi-cavity tool will pay for itself. So a tool which has two cavities is clearly going to be more expensive than a tool with one cavity, but what it means is it's making two at a time, so the manufacturing costs are half. Yeah, and that investment pays back. So these are the sorts of things that we work through with our customers, and we can help them crunch those numbers and work out those things.
Okay, thank you. On to the next one. There are clearly issues with using plastics, both standard and bioplastics. So what does the future hold for sustainability in plastics?
Yeah, well, and yeah, again, I've got to sort of go back to some of the points that I made earlier. No plastic is perfect. Each plastic is a resource, regardless of whether it's a bioplastic or a standard plastic, and it has an impact on the environment and the world that we live in. So we really need to look at the product itself, what that product does, what's going to happen to the product through its life and at the end of its life, and make the best decisions based on the choices of plastics that we have at the moment. But the game changer will come in the future, which is chemical recycling, and this is something that there are a number of academic and scientific institutes around the world working on. It's just not commercial yet, and that's really where you take waste plastic and chemically break it down into its original form. And that's going to change everything in terms of recycling and how we work with plastics for an environmental purpose, because essentially it will ensure that recycled plastic or chemically recycled plastic is as good as brand new plastic. It won't have any sort of negative aesthetics, and it won't have any limitations in terms of its application, in terms of food use, or it won't have any limitations in terms of its color and mechanical properties. So that's really the area to watch. I know that a number of big polymer producers are already looking at commercializing it. It's just not quite there yet.
Okay, thank you. Are there any issues with using family tools?
Yes, so that goes back to my the first question there, actually, Paul, where we talked about how do I know I've got the right number of cavities, and a family tool would be the example of where we have one tool with a number of cavities, and each cavity is making a different part. And again, the problems start to come from balancing the tool and balancing the flow of material through that tool to deliver what we need for each of those individual products. I often sort of talk to customers about injection molding works best in binary numbers. Yeah. And that's because it's very easy to take a flow of plastic and then divide it into two, and then divide that into two, and so on and so forth, and keep that flow equal. But where you have a part which perhaps weighs 3 times more than another part, or has a section thickness that's 3 times thicker, that becomes problematic, and often it can lead to aesthetic problems, such as sinking, which would be a very good example on one hand, or a short where something's not completely filled would be a problem on the other hand. So it does create some technical challenges.
Okay, thank you. And just one last one here. How do I go about designing snap fits instead of using mechanical inserts?
Yeah, so the snap fits are actually very, very tricky to design. I suppose on a basic level, it can be seen as quite simple, but of course, what you've got to think about a snap fit is not only how easily does it go together, but how secure is it once it's together, and finally, do I need to take it apart again? Sometimes snap fits are designed to not be taken apart again, and other times it's an essential part of the function. So there are many, many different ways to do it. There is information on our website which gives some basic advice on designing snap fits. But what I'd say is, give us a call, talk to our designers, and they will help work through that problem with you.
Okay, thank you very much. As I said earlier, if you've written a question and we haven't had time to answer it, we will be handing that on to Rutland Plastics, and they will be able to answer it for you offline. With that, it just remains for me to say thank you very much to Stuart for the presentation today, and to all of you for joining us. Thank you.
Thank you.